Differential equations are equations that involve derivatives. Derivatives represent rates of change, so differential equations essentially describe how quantities change over time or in relation to other variables. They provide a powerful mathematical framework for modeling and analyzing a wide range of phenomena in science, engineering, economics, and other fields. Imagine a car accelerating on a highway. Its velocity, which is the rate of change of its position, can be described by a differential equation. Similarly, the spread of a virus in a population or the flow of heat through a material can be modeled using differential equations. In essence, differential equations capture the dynamic nature of various processes by relating the unknown function to its derivatives. Solving a differential equation means finding the function that satisfies the equation and any given initial conditions. These equations are fundamental to our understanding of the physical world and play a crucial role in countless applications. Differential equations are essential tools in many fields because they allow us to model and predict how systems evolve over time or in response to changes in their environment. By formulating a differential equation that describes the underlying principles governing a system, we can gain insights into its behavior and make predictions about its future state. For instance, in physics, Newton's second law of motion, which describes the relationship between force, mass, and acceleration, is a differential equation. By solving this equation, we can determine the motion of objects under the influence of forces. In engineering, differential equations are used to design and analyze a wide range of systems including circuits, bridges, aircraft, and control systems. For example, the behavior of an electrical circuit can be modeled using Kirchhoff's laws, which are expressed as differential equations. The ability to model and solve differential equations is crucial for understanding and solving complex problems in various scientific and technological domains. Differential equations can be classified into different types based on their order, linearity, and homogeneity. The order of a differential equation refers to the highest derivative that appears in the equation. For example, a first-order differential equation involves only the first derivative of the unknown function, while a second-order differential equation involves the second derivative. Linearity refers to whether the unknown function and its derivatives appear in linear combinations. A linear differential equation is one in which the unknown function and its derivatives appear only to the first power and are not multiplied together. Homogeneity refers to whether all terms in the equation involve the unknown function or its derivatives. A homogeneous differential equation is one in which all terms involve the unknown function or its derivatives. Understanding the different types of differential equations is important because each type has its own methods of solution. Let's consider a simple example to illustrate how differential equations can be used to model real-world phenomena. Suppose we want to model the growth of a population of bacteria. Let pt represent the population size at time t. We can assume that the rate of population growth is proportional to the current population size. This can be expressed mathematically as dp dt equals sine kp, where k is a constant of proportionality that represents the growth rate. This equation is a first-order linear homogeneous differential equation. This simple equation captures the essence of exponential population growth, where the population increases at a rate proportional to its current size. Section 5. Separation of variables. One common method for solving differential equations is separation of variables. This technique can be applied to equations that can be written in the form di dx equals f of x times g of y, where f of x is a function of x only and g of y is a function of y only. The basic idea is to separate the variables by dividing both sides by g of y and multiplying both sides by dx. dy over g of y equals f of x dx. We can then integrate both sides to obtain the integral of dy over g of y equals the integral of f of x dx. Solving the integrals on both sides gives us an equation that relates y and x. This method is particularly useful for solving first-order differential equations. Section 6. Solving the population growth equation. Let's apply the separation of variables method to solve the population growth equation we introduced earlier, dp dt equals kp. Dividing both sides by p, and multiplying both sides by dt, we get dp over p equals k dt. Integrating both sides, we obtain the integral of dp over p equals the integral of k dt, ln of the absolute value of p equals kt plus c, where c is the constant of integration. Exponentiating both sides, we get the absolute value of p equals e to the power of kt plus c. Since the population size cannot be negative, we can drop the absolute value, p equals e to the power of kt plus c, which simplifies to e to the power of c times e to the power of kt. Let p_0 represent the initial population size at t equals 0, substituting t equals 0 and p equals p_0 into the equation. We get p_0 equals e to the power of c times e to the power of k times 0, which simplifies to e to the power of c. Therefore, the solution to the population growth equation is p equals p_0 times e to the power of kt. This equation describes the exponential growth of a population over time, starting from an initial population size of p_0. Section 7. Additional solution methods. In addition to separation of variables, there are many other methods for solving differential equations, including integrating factors, exact equations, linear equations, Laplace transforms, series solutions, and numerical methods. The choice of method depends on the specific form of the differential equation and the desired level of accuracy. Each method has its own strengths and limitations, and it is important to choose the most appropriate method for a given problem. Section 8. Tips for studying differential equations. Studying differential equations can be challenging, but here are some tips to make it easier. Practice regularly. Solving differential equations requires practice. Work through numerous examples to develop your problem-solving skills. Understand the concepts. Don't just memorize formulas, focus on understanding the underlying concepts and principles. Seek help when needed. Don't hesitate to ask your professor, TA, or classmates for help if you get stuck. Use resources wisely. Take advantage of textbooks, online resources, and software tools to supplement your learning. Stay organized. Keep your notes and assignments organized to avoid confusion. By following these tips, you can improve your understanding and mastery of differential equations. Section 9. Conclusion. Embracing the power of differential equations. Differential equations provide a powerful mathematical framework for modeling and analyzing a vast array of phenomena in science, engineering, and other fields. By relating unknown functions to their derivatives, these equations capture the dynamic nature of systems and allow us to make predictions about their behavior. From the motion of planets to the spread of diseases, from the design of bridges to the optimization of financial portfolios, differential equations play a fundamental role in our understanding and shaping of the world around us. By embracing the power of differential equations, we can unlock new insights and solve complex problems that have a profound impact on our lives.